All right, let's get started. So I have another brain teaser for you. This is an old one, but hopefully you haven't all heard it. So there's a swimming pool, and floating on the surface of the swimming pool is a little boat, and inside the boat is a lead brick. Okay? Boat, swimming pool, lead brick. Someone picks up the brick and throws it into the pool, and it settles to the bottom, obviously. The question is, what happens to the level of the water in the swimming pool when that happens? Does it stay the same, go up, or go down? And then why? So this is the way it starts out. The brick is sitting on the bottom of the boat is floating on the swimming pool. And at the end, the brick ends up down here, sitting on the bottom of the pool. So what happens to the level of the water? Three possibilities. How many say it stays the same? Okay, about a third of the class. How many say it goes down? About a third of the class. How many say it goes up? A bit fewer. Okay, so let's take the ones who say it stays the same. Why should it stay the same? Come on, those of you who put your hands up. Why'd you say it stays the same? Yeah? Was it displacing volume? Right. You're on the right track, okay. Another hand. When it was here, what was it actually displacing? How much water was it displacing? Well, when the brick is up here, someone said it displaces a certain amount of water, and the question is, how much water does it displace? And when it gets down here, it also displaces a certain amount of water, and again, the question is how much? And whether those two amounts of water are the same or not gives you the answer to the problem. So when it's up here, it's floating. And what does that mean? What does it mean to float? It must displace an amount of water equal to its weight. When it's down here, it displaces an amount of water equal to its volume. But lead is a lot denser than water. It's 11 times. So it displaces a lot more water when it's up here than when it's here. So the answer is the level goes down. Okay? Supposedly, this problem was given to a bunch of Nobel laureates in physics, and only half of them got it right. So it's a good little problem. Yeah. I don't know if that's true, but that's what I was. I can believe it. I can believe it. Just because you're a Nobel laureate doesn't mean you know everything.
It's true, but you should know that.
Speaking of Nobel laureates, did you guys happen to see Are You Smarter Than a Fifth Grader a few weeks ago? George Smoot. Okay, he won $1 million on that. He's a Nobel laureate in physics. Yep. Yep. Okay, enough fun and games. So, just to remind you, hopefully for the last time, that we're not going to meet here on Friday. We're going to go up to LBL. Again, you can do it either one of two ways. You can walk up there, just head up Hearst Avenue until you can't walk anymore, and that's the lab. Or meet me in front of Corey Hall at about 10 afternoon, and we'll take the bus up together. Okay? This is not a mandatory trip. If you don't want to go, you don't have to go, but I think you will find it interesting. Even if you've seen a cyclotron before, LBL has some unique things that you won't see anywhere else. Cameras are okay. Aaron wanted to let you know that instead of turning in the homework up there, we would prefer that you put it in his mailbox, which is up on the 4th floor of Echeverry, okay? Anytime on Friday is fine. Yes? Okay. Okay. So that's Friday. And then again, just to remind you so no one is caught surprised that a week from Friday there's going to be an exam. Okay. And as I said, it'll cover everything up through and including Chapter 6, meaning the homework that's due this Friday. And I'm not going to give you a new homework assignment this week, okay? Let you off the hook since we're having an exam the following Friday, okay? Okay. Okay, good. Sighs of relief. And what we're going to do today is finish up the discussion of accelerators so that you have a little better understanding of what it is you're going to see on Friday. And that'll complete the material for Chapter 6. Before I get into the discussion of the accelerators, I just want to go back a minute to a little discussion about detectors. We talked the other day about ionization detectors made of semiconductor materials, silicon and germanium. And in case you haven't seen it, this is a chunk of silicon, high purity detector grade silicon. I'll just pass it around. you can have a look at it. I used to have a germanium detector that came out of one that had died, and unfortunately someone, I think, borrowed it and never returned it. But it looks similar to that, it's just that it has a higher density. And then the other kind of detector I mentioned were these bolometers. And I mentioned an experiment that we're working on involving tellurium dioxide crystals. And this is actually one of the crystals we've used in this experiment. I'll pass it around. Please be careful with it. It is fragile. It's a perfect crystal of TeO2 that was grown at a company over in Palo Alto for us. And it's expensive, so please don't drop it and be careful. You'll see it's quite heavy. The mass is about 1.5 pounds. Okay. So let's continue the discussion we had the other day about accelerators, and I'll go back to the electrostatic kind of accelerators for a minute. This is the Tandem Vandegraaff that I mentioned the other day, where the idea is you start out with a gas or something you can make into a gas of whatever compound it is you're interested in accelerating, and you somehow add an electron to it to create a negatively charged ion, which is then accelerated through a small potential difference here. The species of interest is selected by that inflector magnet and then sent into this device, which is the Tandem Vandegraaff. It has a terminal on it, which is set to a very high positive potential. So the negatively charged ions are accelerated up to there. There is a small foil at the center of that terminal called a stripper. And when these negatively charged ions go through it, some or all of the electrons get stripped off. There's then a positively charged ion that emerges on the other side, and it gets accelerated a second time because now it's repelled away from that positive potential. So this is called the Tandem Vandegraaff because the particles get accelerated twice. One important feature of this kind of machine is that the current of the ions that you get out is a direct current. That is, it's constant in time. There's nothing pulsed or intermittent about this. You just have a steady current flowing. And for some kinds of experiments, that turns out to be important. This is a photograph of one of these devices. There used to be lots and lots of these all over the United States. Almost every major university that had a physics department had one of these sitting in their basement. In the 60s and 70s, they were installed all over. For various reasons, most of them have been removed, but now there's one sitting at the Western Michigan University. This is about 20 or 25 feet long. These are big objects. And this particular one can go up to 7 million volts. That means the voltage on the terminal, which is in the center here, can go up to 7 million volts. The way that terminal is charged is with a charging system like this. This is what's called a pelletron. Remember, you have to bring electric charge from ground up to the terminal and remove the charge and place it on that, that terminal. And this is the way it's done. There's actually a belt which transports the charge from ground up to the terminal. It's removed here. And that's how you charge it up. And you want to have a very uniform electric field all along the beam path. So the way this is done is you have a series of electrodes with resistors in between them. So you have a very uniform voltage gradient all the way up there for the ions to be accelerated in a very uniform way. And this is a photograph of these electrodes. These are glass plates with resistors tied between them. So you have a very nice voltage increment across each gap. Okay, and then we talked about the linear accelerator, the LINACs. This is now an alternating current machine. The particles come in little bunches, and the idea here is, let's say you start out with a positively charged ion, you take a hydrogen atom and you remove an electron, so you have a proton, and you put a negative potential here using a sine wave or RF generator. So the proton is accelerated up to here, but once it gets inside that hollow tube, as I said previously, it can't see the electric field. And so you switch it from being negative to positive. So when the proton emerges over here, it's repelled away from that electrode. And meanwhile, you've made this one negative, so it's accelerated there. And every time it goes across the gap, it gets accelerated. But this only works if the protons come at the right interval in time so that they always arrive at the gap when the potential is in the right direction to accelerate them. So you get bunches of particles that way. And because the velocity keeps increasing, the length of these tubes have to get longer and longer as the particle gets accelerated. And I mentioned that there are big ones of these in various places around the world. This is at the Los Alamos National Lab in New Mexico. There's an 800 million electron volt accelerator there. It's about, I don't know, half a mile long, something like that. Okay, it's on a mesa at the Los Alamos lab. It accelerates protons to 800 MeV, and what it's currently used for mainly is it takes those protons and smashes them into a target of tungsten and makes lots and lots of neutrons. And the neutrons are then used for a wide variety of research applications. And then I mentioned the Stanford Linear Accelerator across the bay. This is an enormous accelerator. This is 2 miles long. And the beam actually crosses underneath Highway 280. So if you've ever driven down Highway 280 from San Francisco to San Jose, that's the road in the picture there. And you look down and you go right across the beam. Okay? And it produces up to 32 GeV, 32 billion electron volts, electrons and positrons. So these are very, very big machines. I mentioned the cyclotron. That's what we're going to go see. This is a device invented by Ernest Lawrence. He was a faculty member here at UC Berkeley. And he came up with this idea in 1929. And the idea, just to reiterate, you start out with a positively charged ion. Remember, you have to have some kind of electrical charge on these things to get them to accelerate. So in this kind of machine, it's a positively charged ion that's used. You'll see the ion sources which are installed at the 8-inch cyclotron. You might not think this is a big deal, but the ion source is actually the key to making these things work, especially if you want to accelerate heavy ions, not just protons or alpha particles, but suppose you want to accelerate uranium ions. Okay? You start with uranium metal, let's say. You need to remove an awful lot of electrons from it to get a high enough charge state that you can actually accelerate it to the high energies we need to make nuclear reactions happen. And LBL has been one of the world leaders in developing the ion sources you're going to see that allow this to happen. So you produce a positively charged ion, you get it down to this point. Remember, these are hollow copper Ds. They're conducting metal tanks. There's a slot inside them. You put a radio frequency voltage on there. So again, you have a positively charged ion. You make this D negative and this D positive initially. So the ion gets accelerated toward the D. It goes inside that slot. And inside the slot, it can't see the electric field here, but it sees the magnetic field, which is pointing into the board. There are enormous magnetic pole faces that surround this top and bottom. So the ion moves in a circular trajectory with a radius that depends on its charge and mass and velocity. We'll see the equation in a minute. And while it's in there, you play the normal dirty trick. You change the sign of the electric field. So you make this one positive, that one negative. So when it gets over here, it gets accelerated. And what happens is every time it goes through that acceleration, its velocity increases, and hence the radius of curvature increases. But as we're going to see in a minute, it always takes the same amount of time to make half an orbit. And so with a constant voltage, constant frequency voltage, the particle always arrives at exactly the right time to get accelerated. Its orbit gets larger and larger in radius. Eventually it gets out to the edge here where there's an electrostatic deflector that sends it out of the machine and out to the experimental area. So again, this is a slightly enlarged drawing. So here are the two Ds in between the pole faces of the magnet. So you've got a uniform magnetic field, meaning uniform in radius. Under those conditions, if you have a particle with charge Q and velocity V moving through it, this is the force equation. QVB equals mv squared over r. In other words, the magnetic force on that particle is equal to the centrifugal force. And so if you then say, how long will it take it to make half an orbit, half a complete orbit? Well, in half an orbit, the distance it travels is pi r. 2 pi r would be a circumference, so half a circumference is pi r. And its velocity would be v, because we're assuming it's a constant velocity while it's just coasting through the d. So pi r over v we can solve for using this equation. It's m pi over qb. And notice that now the time it takes to make half an orbit is independent of r. That was the thing that Lawrence figured out, that the frequency could remain the same. And so the frequency is 1 over 2t, where that's the time, and that's qb over 2 pi m. This is what's known as the cyclotron frequency. So when an experimenter tells the operators at the cyclotron that he or she wants a certain ion, let's say it's neon, and they want 200 MeV neon ions, the operators will use a computer program that basically solves this equation and tells them what cyclotron frequency they're going to have to run, meaning what frequency RF signal they're going to have to send in to make sure that those ions come out with the correct energy. And in terms of calculating the energy, these are what are called low-energy nuclear physics projects these days. And what that means is that for most applications, we can get away with mechanics. We don't need special relativity. And so I can say then that the kinetic energy of the particle that emerges from the cyclotron is 1/2 mv squared. And going back to the force law we just wrote down a minute ago, that's q squared, where q is the charge of the ion that's being accelerated, b is the magnetic field between those pole faces, r is the maximum radius, meaning the diameter of the pole faces, and m is the mass of the ion that's being accelerated. So for a given cyclotron, for a given machine, B and R are just constants, okay? They're given by whoever made the machine. And so we can combine them into something called K. It's a constant which defines the particular machine you're working with. And then the maximum energy is K times Q squared over M. And this is where the ion sources become important, because that Q is the electric charge on the ion that's being accelerated. So for a given cyclotron, for a given machine that you have, the higher the charge state you can make that ion, the higher energy you can get. And that's why it's important to rip as many electrons off the atom as possible. For LBL's cyclotron, it turns out this K factor is approximately 130. And that's because of the size of it and the maximum magnetic field that can be applied. So if you use this equation and just calculate what that means for something like a deuterium ion, okay? So for hydrogen 2, the maximum charge is 1. It's only got 1 electron. And its mass is 2. So according to this equation, then 1 squared is 1 divided by 2. I get 65 MeV. And that turns out to be true. It's the highest energy deuteron you can get. For helium-4, Q squared happens to be 4, because we've got helium, 2 electrons. I remove them both. So it's 4, and the mass is also 4. So I get 130 MeV. And then for what we call heavy ions, meaning all the elements heavier than helium, carbon, oxygen, silicon, whatever you want, the maximum energy you can possibly get from this particular machine is 32.5 million electron volts per atomic mass unit. So if I'm talking about, silicon 28, A would be 28. And the total energy of that ion would be 28 times 32.5. And that's just a function, again, of the size of that particular cyclotron. This is, again, low-energy nuclear physics these days. The machine I was talking about earlier, this is high-energy physics, okay? And there are things in between. Okay, so if you want to go to higher energies for some reason, the cyclotron has an inherent limitation. That you saw that the maximum energy depends on the strength of the magnetic field I can get and also the radius. So if I want to go to much, much higher energies, I have to make the machines bigger and bigger in size, in physical size. And I also have to increase the magnetic field. And those two things get to be prohibitively expensive. In particular, if you wanted to go to GeV kind of energies, billions of electron volts rather than millions of electron volts. And so back in the 50s, people realized this limitation of cyclotrons and came up with ideas for other kinds of accelerators. And one of them, which was developed, is called the Synchrotron. And it uses the same basic concept as the cyclotron. Namely, you're going to apply a radio frequency voltage to accelerate particles, and you're going to confine them to more or less a circular orbit with a magnetic field. But now you're trying to do this at very, very high energies. And so in the synchrotron, what happens is you again start out with your positively charged ions. You put them into this ring, and they get accelerated across a gap. When the particles go across this gap, they get accelerated through this RF potential. And you have a magnetic field going into the board. But what you try to do is to confine these ions always to the same radius orbit. You don't let them spiral out as you do in the cyclotron. Because they're accelerating, they're harder and harder to bend into that same radius orbit. So you have to increase the magnetic field. And so in this device, what happens is you ramp up the magnetic field as the particles are spiraling around in just such a way that you keep them in the same radius. So they always orbit inside this nice ring in here. And as a result, again, you have to pulse this thing. You dump in a bunch of protons, you let them go around the ring, you apply the RF voltage, you ramp up the magnetic field, and when they finally reach the maximum energy, you bring them out somehow. Okay? And this allows you to go to much, much higher energies than you can get in a cyclotron. One of these devices was built at LBL back in the 1950s. Okay? It's currently being dismantled, but in 1955, this is what it looked like. This was a device known as the Bevatron, and it was the biggest synchrotron in the world at that time. You probably can't recognize much of LBL from this photograph. Back in those days, it was mainly empty space on the hill. What happened was Lawrence started out building his accelerators here on campus. And as I mentioned the other day, the first one he made was yay big. And he kept making bigger and bigger ones because of that equation we just went through, that in order to get to higher and higher energies, they had to get larger and larger. And eventually he outgrew the LeConte Physics Hall, and the university, which owned the land up the hill, said, go up the hill and build your laboratory up there. And so he did. And he built ever larger cyclotrons. The largest one he ever built was 184 inches in diameter. That machine got torn out in the 1980s. They saved the dome of it, and you've probably seen the dome. Underneath it now is what's called the Advanced Light Source. It's a synchrotron that accelerates electrons up to a GeV to make X-rays. But that originally housed the 184-inch cyclotron. So in 1955, the Bevatron was built, and it was actually built to do one experiment. Very interesting experiment. These are a couple of the guys who helped build it. This is Edward McMillan and Mr. Lofgren. This is actually the ring of the synchrotron. Underneath all this concrete is where the ring is. The concrete's there to shield people from the enormous amounts of radiation it could produce. The one experiment it was designed to do was to make a particle which was believed to exist, but no one had seen it yet. It's called the antiproton. So remember, back at the beginning of this class, we talked about the idea that for every particle there's an antiparticle, and now we generally accept that that's true, but in 55 it wasn't so clear that that was actually true. The only real antiparticle that had been discovered up until then was the anti-electron, or the positron. Some people thought that that was an exception, that there wasn't a general principle that all particles would have corresponding antiparticles. And to establish that, it was important to see if there really was a particle called the antiproton. So these guys decided to go ahead and try to make antiprotons. And the only way they knew how was to smash things together and hope that by chance an antiproton would get produced. And the way they tried to do it was to take a proton and shoot it at another proton. And they had some ideas about conservation laws, namely that you had to conserve not only energy and momentum, but you had to conserve electric charge. And there was this quantity that people had thought about that somehow distinguished a particle like a proton or a neutron from an electron. Okay, other than its charge and mass, they thought there might be some other property. We now call it baryon number. So protons and neutrons are what are called baryons. And we think that the number of them in the universe is more or less a constant. So they wrote down this equation thinking, okay, if I have enough energy, I can take my two protons, I end up with two protons in the end, and I create a particle-antiparticle pair, a proton and an antiproton. So that's what they were attempting to do. And the question is, how much energy does it take to do that? Okay? And you might think, well, I've got two protons over here, I've got four protons over here. I just have to add two extra proton masses, and that's enough to do it. And in the center of mass, that would be true, but not in the laboratory. Because remember, I'm going to shoot a moving proton at a stationary one. The collision is going to produce these extra particles. And because the incoming proton had some momentum, the final particles can't be at rest in the laboratory. And so I need to provide more energy than that to allow these final particles to move. So the question is, how much energy do you need to do it? And here, we're going to have to use special relativity. Because now we're going to talk about energies which obviously are comparable to, in fact, greater than the rest mass energies of the particles we're interested in. So we got to use relativistic kinematics, and a very useful quantity in relativistic kinematics is something called the invariant mass. If you remember the way energy is defined, it's E squared is P squared C squared plus M0 squared C to the fourth. That's what we call the relativistic total energy. So if I take E squared and I subtract P squared C squared from it, I get the mass of whatever system I'm talking about. And it turns out that mass doesn't depend on which reference frame I measure it in. That's why it's called the invariant mass. So I'll use this in a minute to help me go back and forth between the center of mass frame where it's easy to do the calculation and the lab frame where it's not so easy, because x is the same. So if I go into the center of mass, what that means is I've got a proton and a proton coming in at each other with equal and opposite momenta so that the total momentum is 0. And in that reference frame, the 4 particles that get produced, the 3 protons and the antiproton, can all be at rest. Okay, because the total momentum before the collision was 0, therefore the total momentum after can be 0. And if all 4 particles are sitting there at rest, then it's easy. The momentum in that reference frame is 0, and the total energy is just the sum of the rest mass energies of those 4 particles. That's just 4 times the mass of the proton times c squared. And since x is just the square of that quantity, according to this equation, x is 16 mp squared c to the 4th. Okay? And that's independent of the reference frame. Now I have to go back and look at the lab frame, because that's where I'm designing my experiment. My machine's going to be in the laboratory frame. So in the lab frame, I've got a stationary target proton and a moving projectile. So one proton carries all the momentum. So in the laboratory, the total energy is the sum of the energy of the stationary proton and the moving one. For the moving one, the total energy can be written as gamma, the relativistic gamma factor, 1 over the square root of 1 minus v squared over c squared, times the rest mass energy of the proton. And then the stationary proton just contributes its rest mass energy. So the total energy in the lab is 1 plus gamma times the rest mass energy of a proton. I then have to calculate x, that invariant mass, which means I square the energy in the lab frame, and I subtract p squared c squared from it. So I square 1 plus gamma, and I get 1 plus 2 gamma plus gamma squared minus p squared c squared. But then I remember this whole idea of the invariant mass is that for a single proton, gamma squared mp squared c to the 4th minus p squared c squared equals its rest mass. So I can solve for gamma. I can solve for x, rather. X is 2 plus gamma, 2 gamma plus 2 times the rest mass energy of the proton. That equals the invariant mass in the center of mass, which we already solved for, 16 mp squared. So now I can solve for gamma, the relativistic factor. It has to be 7. Okay, gamma has to be 7 to provide enough energy. So the kinetic energy of that one moving proton in the lab is gamma minus 1, which is 6, times the rest mass energy of the proton. So what these guys figured out is to make this reaction happen, you need to have protons of at least 5.63 GeV, okay, to initiate the reaction to allow both momentum and energy to be conserved. So they weren't quite sure of all this, so they made the machine to accelerate 6.2 GeV protons, so they could be above it. Okay? And this is what they found. So they built the machine, they accelerated protons on protons, they measured a new negatively charged particle coming out of the reaction, and I'll show you some of the data in a minute. And they measured the probability or the cross-section for that to happen as a function of the energy in the beam, in the moving proton. So when they were down at around 4 GeV, in those days they called it BeV for billions of electron volts. Since then we've gone to giga GeV. So down at 4, 4.2, they didn't see anything. When they got up to 5, they started to see something. And when they got up to 6, it got even bigger. Okay? So they seem to be seeing a threshold of a reaction that had about the right energy compared to the calculation we just did. They measured the mass of these outgoing negatively charged particles by deflecting them through a magnet and measuring the charge to mass ratio. And they could tell they were negatively charged because they bent in one direction, whereas the positively charged particles bent in another. And what they found was this new particle they had discovered had just about the same rest mass energy as the proton. And so they decided, in fact, they really had discovered the antiproton. And one of the ways they convinced themselves that this particle really was the antiproton is they would then separate it out from the rest of the particles that got produced and allow it to come to rest in photographic emulsion. And this is what they would end up seeing. So an antiproton would come in, and you're going to ask me which track is actually the antiproton. I think it may be that one. It comes in like that. It's a ionizing particle, so it produces a track in the emulsion. It comes to rest at this point, finds another proton, and the two annihilate each other. Okay? But because these are protons and antiprotons rather than electrons and anti-electrons, you don't just get photons being produced, you get other kinds of what are called hadrons, particles that interact via the strong nuclear force. These tend to be pions, pi mesons coming out. And this event is called an annihilation star. It's a signature that you actually had an annihilation right here. And this was one of the, again, convincing pieces of experimental evidence that these things really were antimatter. And over the years, people have produced other antinuclei. I think the heaviest antinucleus that's been made to date is helium-4. So they've made antihydrogen, antideuterium, antitritium, antihelium-3, and antihelium-4 in the laboratory. It's very, very hard to do that. There are lots of experiments going on in space now looking for antimatter that might have been produced in extraterrestrial environments. It would be very interesting, for example, if you ever saw an anti-iron nucleus. Because it turns out iron gets made in stars. We'll see that in a few weeks. And if you saw an anti-iron nucleus, that would mean that there are anti-stars out there. And that would be extremely interesting. So people are looking very hard. Maybe you guys will find them. Okay. And just to finish the story on the antiproton, these are the gentlemen who led the experiments. This is Owen Chamberlain and Emilio Segre. They were both faculty members right here on campus. And as you can see from over here, in 1959, they each received the Nobel Prize for that work. It was a very, very important experiment. Once the Bevatron had done this experiment, it was basically outdated. Okay? Other people decided to build bigger machines elsewhere in the world, and for many, many years, the Bevatron really had no function because there were higher energy machines elsewhere that could do more interesting high energy physics. What happened was a nuclear chemist by the name of Albert Ghiorso at Lawrence Berkeley Lab figured out that you could use it to do a new kind of nuclear physics by accelerating heavy ions to these relativistic energies. And what he and the folks at LBL did was to couple a low energy nuclear physics machine that could accelerate anything from hydrogen up to uranium to the Bevatron and accelerate uranium nuclei to GeV per nucleon energies. And they invented a whole new field of science called relativistic heavy ion physics. And for many, many years, that's what the Bevatron was used for. It's now being dismantled, as I said. But other synchrotrons were built elsewhere in the world. This is one that's outside of Chicago at the Fermi National Accelerator Laboratory. You can see that this one's enormous. It's 1,000 meters in radius. Okay? So this is nearly a mile. And inside the ring, they actually graze buffalo. There's a lot of land in here. That's an aerial photograph of it. And this is the largest accelerator in the US right now. It can accelerate things to very, very high energies. And it's mainly used to do proton-antiproton collisions. Okay, now we know that antiprotons exist. In fact, we can make them very easily. And now we can watch what happens when protons and antiprotons collide. This is another very large accelerator facility. This is in Switzerland. It's called CERN. This is a proton synchrotron. And this is also the location where the Large Hadron Collider is being built that you've probably read about. And this thing is something like 20 miles in circumference. Okay, these things have gotten to be enormous. And that's, again, to allow you to get to very, very high energies. And this is the way they do the colliding beams. So, for example, you could have protons going around in one of those tubes, like that, and have antiprotons going in the other one, and at this point here you bring them together and you watch what happens. Okay? So it's no longer the case that you have a stationary target and a moving projectile. In these kind of facilities, everything's moving in the colliding beams. And one of the locations where we do this in the US is at the Brookhaven National Laboratory on Long Island, and there's a facility there called RIC, the Relativistic Heavy Ion Collider. And it's a very large synchrotron. That's what that ring is. And in that, they accelerate nuclei. And again, you can have anything from hydrogen up to, I think, gold is the heaviest kind of beam they currently run. And they'll put gold nuclei moving in one direction and gold nuclei moving in the other direction. And they bring them together and watch what happens. And when these two gold nuclei hit head on, you get something like that. So that's a photograph of the particles that get created when two gold nuclei hit head-on. So one gold nucleus was going that way, the other was coming out of the board at it. They collided, and each one of these tracks represents a single charged particle that got produced in that collision. And you can hardly tell how many there are, but from the folks who do this for a living, they'll tell you there are about 10,000 tracks in that image. Okay? And if you think about it, you know, in the two gold nuclei, each nucleus has about 200 particles in it, 197 to be exact, protons and neutrons. And if you think the worst thing you could do is totally dissociate it, you would expect to have at most 200 tracks, and in fact, 400 tracks, and you wouldn't have 400 because the neutrons wouldn't make a track at all since they're electrically neutral. So maybe you would expect 200 tracks. How do you get 10,000 coming out? Okay, these are particles that got produced in that collision because of E equals mc squared. There's an enormous amount of energy. There's hundreds and hundreds of GeV of energy in the kinetic energy of those two particles, and almost all of it gets converted into rest mass energy. And that's what you're seeing here. So the people who do this for a living study these tracks and try to figure out what actually happened in the collision. Okay. And I think that's it. Yeah, question?
Why are they dismantling the Bevis?
Because essentially that higher energy and more useful machines got built elsewhere. So the Bevatron, as I said, invented this field of the relativistic heavy ion physics. It was limited to about 1 GeV per nucleon, and most of the physics that could be done with that energy was done in Berkeley. As a result of that, people decided to build another bigger machine, and largely because of the real estate available here, it didn't make sense to do it in Berkeley. You know, the laboratory is a great place, but it's very limited in terms of real estate. It's also built on a very steep hill, and it's sitting right in the city of Berkeley. So to build the next generation relativistic heavy ion machine, they went to Brookhaven. And there was just land available there, and it's further away from large metropolitan areas. It made more sense to do it there. So this is really the next generation machine based on the Bevatron. Yeah?
Why did they choose like 88 inches? Obviously, they're not going to choose a huge one. That's like
Right. So Lawrence had been making successively larger ones. So the first one was about 4 inches or so, and then they went to 18. The largest one he built on the campus was 60 inches. That actually was over in LeConte. Once it got larger than that, they couldn't accommodate it. Why exactly 88? I don't know. Oh, it's a good question. Maybe you can ask someone up at LBL. I think it really had to do with the physics that people wanted to do and what diameter machine you needed to reach the beam energies they wanted. So they wanted something like 100 MeV alpha particles, roughly. And Lawrence and his colleagues figured out 88 inches was the right size to do that. When they built the 184-inch cyclotron, that was to get them to much, much higher energies. Originally, that was actually used to separate uranium for the Manhattan Project, turns out. Later on, they ended up making beams of alpha particles of about 500 or 600 MeV, which got used at the end of its life to do retina cancer treatment. We'll talk about that later. They would actually take a beam of alpha particles and shoot them through the pupil of someone's eye and arrange it so that it would come to rest in the retina and produce damage to the cancers in the retina. So it depends on what you want to do that determines how big a machine you need. Other questions? Okay, now let me just warn you a little bit. There's a very good chance you won't actually see the cyclotron on Friday. And the reason is when it runs, it produces a lot of radiation, and you can't actually go into the vault where it's located. If the machine is running, you won't see it, but you'll see what happens as a result of it running. If it isn't running, then we'll go in and actually see the machine. But the drawing I showed you is pretty much what you would see if we went in there. Okay? There's still lots of other interesting stuff. Okay, see you Friday, either up at the lab or in front of Corey.